Are you guys recording? Oh yeah.
There it goes, the recording.
Good. So yeah, I wanted to, I guess I heard some people voicing some interest in I guess Dr. Bruce a long time ago about how to do, sound at the same time and the microbit or asynchronous playing a sound while you're backing up and like a beep beep sound with the microbit robot, and then other type multitasking things that you might do with that robot. And so I've been using it, some techniques in different projects where it's available. So I'm going to cover first, just talk about Arduino and how you can do, how we do multitasking there, because we kind of have to do multiple tasks, but we don't do them with a very sophisticated way. And then I'll talk about what I did with the Lego Mindstorm NXT with Robot C, and that has a legitimate multitasking firmware. And then the microbit as well has. So let's start with multitasking in Arduino programming. Essentially, you just take the things you need to do and you put them in your main loop one after the other. That's generally the way. That's the way we have to do it. And unfortunately, this is a bit cumbersome and a bit hard to read. But more importantly, it's difficult to control how often and how much time is spent on each one, because they're just one after the other. For hardware-related updates, though, you can use interrupts, which is nice. So here's a piece of code from, sorry, there's going to be code in this, but I'm going to keep it to just slides and not looking at a code viewer or anything. But I've edited the code, all these code slides, to kind of highlight just the parts and delete the rest. So here's a piece of code from my line following program for the Arduino, and here's the loop, and here's an example of kind of tasks that we have to do. And essentially we're doing multiple tasks just in a one after the other for each iteration through the loop. So for instance, I'm looking for IR codes from a IR transmitter to do something like stop or go, and then I'm getting a color from a sensor, and then updating an LED. Well, that's not shown, but this is getting the color, and then we do various things like handle the line following, look for the color change, look for the end green oval, update the motors, and then the whole thing repeats. And so in this case, there's no interrupt. It's just polling, like every time through the loop, get the data. And I don't even know how often that calls. Is it 160 times a second, or and then if one of these routines down here, like handle line following, takes more or less time, then it's going to be a different amount of time to the next call to something else. So it's not very consistent, but it works. And here's a case where we do use an interrupt. So the only kind of true multitasking kind you can do is you can have an interrupt handler, which will call into another function. So here we have, here's the setup. You have an interrupt pin, you have a variable which you have to declare volatile, by the way, because that means it's not going to be optimized. The compiler will assume that it won't cache it anywhere, because it could be changed in an interrupt. So You have an interrupt service routine, and you can see all this does is set a value of data ready to true. And then you set in the setup, you have you set your pin, interrupt pin. In this case, it's a pull-up situation, and then you attach the interrupt, and it's a falling when the signal falls. Then it's going to go to this routine called ISR. So that is happening. That's through an interrupt, and once the hardware signals that line, then that routine will get called, and then in the main loop, we check to see if the data is ready once per loop, and then we get the raw data, or we get the data, and then we clear the interrupt. So this way, it's a little more predictable, because this if data ready takes very little time compared with the get raw, get raw data here, which is polling every time, and this actually does the whole routine, it does the whole time integration and everything to get that data, whereas this and you can only call it so often, and this one, it just the data comes in, it hits this flag, and then you get it. So that's an improvement, and here's just a little demo of, or just to recall what that code does. So it essentially it's looking at the data, it's looking at the color, and it's continually updating those LEDs, and of course moving along to do its logic. And then I can look for the color blob at the end. So this is from an old example, and I'll move on to. So yeah, any questions so far? That's sort of the state of kind of the way we do currently. To do multiple things by just executing them one by one, and it can work. It's just can be difficult to debug and get it all kind of working with the right amount of timing and everything, if you know what I mean. So if there's no other questions, I'll move on to the central concept of multitasking, the two different kinds, parallelism and concurrency. And I'll just say, running two things in parallel means they're truly running at the same exact time, which requires a multiple CPU or execution unit. Whereas running multiple tasks or threads concurrently just means they're being handled at the same time. And the CPU instruction level is only one is executing at any one instance. So you're just going from one to the next, and but you really only have one CPU in this case working on those different tasks. Is that pretty clear, the difference? Concurrency multitasking is what I'm going to focus on here, because most of the time we only have one CPU in our robots. I mean, most of these simple ones. Parallelism is good, but we'll focus on this for now, and that's what I've done. I mean, this is what I've been working on. So one solution to run multiple tasks is this concurrency multitasking, and it gives each task, there's a system there, a runtime, that gives tasks a turn one by one to execute their instructions. So, and it could be round robin and other techniques, other algorithms. So there's two different kinds. There's this older kind called cooperative, and then preemptive is the state of sort of the normal way. And preemptive means that it will take over. The system will give you some time and then take it in between instruction, essentially in between lines of code, it will say, "Oh, you're done. I'm moving over to the other one, this other guy now." And a simple, yeah, this is very, very historical importance here. The Apollo guidance computer in the 60s used preemptive multitasking with priority multitasking, essentially, to help land on the moon. And it actually really worked, and it even had an error. And the error simply was safe. It was just throwing out the least important tasks, which were not critical for the landing. And so that's been around for a long time. And here's kind of what I said, or more in a more full fashion here. Cooperative multitasking means that each task would give up control to the other tasks, other queued tasks, voluntarily or with a system call. So you would you'd have some code, and then you make a call like sleep or some other call, and then it gives up control, other tasks are done, and then it will come back to you after that is done. And that's the cooperative. And then a lot of systems used to use just cooperative, where if you didn't make that system call, then you would hog the CPU, and that was considered bad, in most cases, because then other things like Windows wouldn't be updated, etc. The early Macintosh programming was like that, that I worked on. So preemptive, with preemptive multitasking, there's a scheduler. It gives you an execution time slice, and at its end, at the end of this time slice, it suspends the task and resumes another task, and so on, based on a priority system. So you could be a high priority task, or a mid, or a low, and it would decide which one to go. And if they're at the same priority, then it just round robins them, gives them equal. It gives them equal time in a cyclical fashion, like a linked list, going around the linked list. And also, preemptive multitasking inherits the cooperative model, so you can still explicitly give up control when you're in the when you're in a preemptive system. So you can still make that system call like sleep or other calls, and it will give up control and then come back to you later. Any questions about that before I move on? I don't know if people may know a lot of this, or it might be new to some. I'm not entirely sure. This is kind of computer sciencey.
Thanks, it's great.
What's that?
I said, thanks, it is great.
So my first project that I'll talk about was with Robot C, and Robot C is, I bought a version for the NXT, for the Lego Mindstorm, which includes the NXT and the EV3 compatibility. And it also came with the VEX. The license I bought came with VEX support, although I have not built a VEX robot, VEX Cortex and IQ. And you can get a Robot C for Arduino is free. It's an it's an older version, but it actually, I may try it out. I didn't realize I could do multitasking with an Uno, like actual real, or up to 3. It allows you to do up to 3 concurrent tasks on an Uno without actually using the new way, or the way I'm going to show you, instead of the old-fashioned way. So here's what Robot C provides, and I wrote a long program. I had in Robot C to do the my robot called Total Cans Recall, which moved around. It was the Clean the Room contest that that we had, that Bob did. Now, so what it does is Robot C has a custom firmware that takes over, that is downloaded to the NXT or these other devices, and with a preemptive multitasking. So it does take a little memory, but I was able to fit this huge program in, so I don't think it's too bad. And so you have functions such as start tasks, stop tasks, of course sleep, wait 1 millisecond, which wait 1 millisecond is essentially a form of sleep, and then a priority variable. So you can make any function into a task by putting the task keyword in front of it. And the main function of the program is essentially always a task. That one is like the primary task is the task that launches all other tasks. And then, so I'm going to talk about this one I wrote here called Stop After Black Line. That's also a task. So from your main program, you can start other tasks, stop them, and then the system will automatically, and then you can give up control voluntarily, or you can not give up voluntarily, and it will just take control in between any of the lines of your code. It could happen at any moment, which you have to be aware of. So this first routine is called Stop After Black Line. So this is a task. So this is to stop a robot when a black line is crossed, and that's used when returning the can to the recycle area. So what I want to do is I want to move the robot forward and then detect the beginning of the black line, and then keep going forward until the other side of the black line. This is a black piece of tape. So you see my long, I actually really do use long names like this. Actually, it was even longer, but sensor, floor tile, black tape, threshold. So that's like a value. And so if, we don't have to go through all this, but essentially just what I said, if it hits the black, then it goes into this second while. The whole thing is an infinite loop. Whoops, infinite loop. This task will continually run with an infinite loop, although at the bottom here you'll see it says wait 50 milliseconds. That's what that means, which is not absolutely necessary, but since I don't need to do this operation that often, it's best practice to go ahead and, to give up that much time, and then only, you obviously only want to execute your task as often as you need it, not as often as the system will allow it, right? So I only need this to execute this often, and so if it gets into it sees the beginning of this black line, and then it keeps going until it sees the other side, and then it stops the robot and then returns. So that's all this does. Now, oh, I might have put this out of order here. So in the main, and before I show you that video, in the main function, the first thing I do is, we'll get into this in a minute, this localized tab. So this is starting one task here. And then I've cut out a lot of code, but there's a lot of stuff happening here, a lot of logic. But after the can is captured, and if it is captured, I took away the if, this is the code I want you to look at. Start task, stop after black line, and then I issue the command go to destination home. So I'm telling this other task to start up, so that task will now be given time, essentially, every so often, and then when this finishes the home, then I stop that task, and so that, And the purpose of that task, as you see here, is to stop the robot when it gets to a point. And of course, I can check to see if the robot stops in other code. So if this guy stops it, then I'll know that in the other code. And this is the only thing that can stop it, for instance, in that situation. So so the output, essentially the result of this routine here, the purpose is to stop, and then then I can continue after that. And then I don't need the task anymore, so I can stop it. So because it's an infinite loop, I can just stop it. And then I know I've done one more can, and then here's another example of this stop all task. Once I've hit all the cans to collect 3, then I stop all tasks, which really shuts the program down, essentially. So take a look. I wanted to show you specifically this part. So right there, it crossed the black line. I can do it again here. So right there, that was the actual code executing, crossing that line. And it's in at the same time as other stuff is going on, obviously. And that's the key to all this, is the ease of programming, or the design of the program just is easier to read, understand, and organize, and even debug, I would argue. And so now and then, well, I guess I could show one. Let's see, the last one here. Oops. That one, I need a claw that can open and close to get rid of that problem. So so that, and we'll come back to that. But what I want to show you next is a little more of the details of this. Just shows you how you can have multiple things running. But what if you have to coordinate between tasks? So you need to be able to communicate somehow. How about a global variable? That's the simplest way. I have this routine I just alluded to, called a localize. It updates, its purpose is to update the current pose of the robot. And this variable, this global variable, other tasks can read that variable and know where the robot is. So this localize routine runs on its own infinite loop, and concurrently runs while any other behaviors can go on. But to remember here, this G current pose is made up of 3 values, X, Y, and theta, right? So on a flat plane, it needs to know where the robot is in its direction. So what would happen if the X value is updated? Then the scheduler suspends the task and wakes up another task that uses all 3 values before the localized task is resumed. Oops, you can have X has been updated, but Y and theta are the old values still. So now you've got inconsistent data. You've got an incorrect location there. So you have to prevent that. So here's a real basic introduction to the synchronization mechanisms that are commonly used. The mutex lock and the semaphore, in this case a semaphore or binary semaphore. So this lock protects this critical code, like changing a global variable shared between tasks. So what you want to happen is all 3 values are changed, the X, Y, and theta, before anyone else can read them. So that's what you do. So that's what this locking mechanism can allow you. And the mutex lock has just lock and unlock. And so you can lock you can issue a lock, which means that no one else and everyone, all the other parts of the program have to. It's a convention. They have to use this lock to get at the data. They can't just read that variable. That would be essentially a bug in your code. You must use, if there is a mutex lock associated with that global variable, then you need to attempt to lock that before using the variable. And if you try to lock and someone else already has it locked, the code will block there. It will wait until it's unlocked. And that's the basic concept. Then when you when you unlock, someone else can access it. So a binary semaphore is essentially the same, used as the same purpose as a mutex lock, and that's what we're going to use in this code. They actually named it incorrectly. They should have called it a mutex, but you'll see that in a minute. And there's also something called a counting semaphore, which can manage the use of multiple resources. So that has a wait and signal. I won't go into that, but it's very common for the use of what's called the consumer producer-consumer problem, where you have multiple resources, and one routine is producing them, another's consuming them. But that's what this is very useful for. So here's the localized task. It's just, this task is to keep track of the XY position and heading of the robot using dead reckoning. So here's just a simple part of it, or just a reduced part. So this is the code that was available in that robot C. They have a basic binary semaphore, but they called it lock and unlock. It's really kind of the wrong term, but it's supposed to be wait and signal, but okay, who cares? You know, it's not that important. It's essentially the same thing as a mutex lock. And so what happens here's in this main code, this code for localize, I update the odometry by giving the current pose and then new pose, and then a new pose comes back. A new pose is being set here, and then what I do here is so yeah, this routine returns a new pose, this update odometry. But before I can change the global, the G current pose, this current pose is a local variable. So I'm sorry, this current pose is the semaphore. So I lock this semaphore, and then I can assign the global variable, and then I unlock. So this is what you call a critical code protection. So that when I'm doing this assign, which is 3 lines of code, assign has to do 3 things, and I don't want any interruption. I don't want anyone to read the value until all 3 lines are done. So that's what's happening here. Anyone else who's trying to read will also have to have the same code, lock and unlock. So the lock waits until it's not locked, and then the unlock will signal I'm done. And so that's how this assigns new values to the current pose without interfering with someone else who's in the middle of reading. And with, like I said, with multitasking, preemptive multitasking, any point at in between any line of code, you could switch to another process, to another task. So that's why you have to set it up so that you're ready for that. But again, preemptive only gives a certain amount of time, so it will allow a certain amount of time in milliseconds to execute, and then it will say, okay, I'm taking away control, and giving it to somebody else. So it won't wait there forever. Even if you're in a lock, it's going to wait, but the preemptive system will say, okay, even though you're stuck here, I'm going to the other guy now. And so here's what the go to destination, this is called by main, as you saw earlier. This is a user of the current pose. So it locks using the semaphore, the current pose semaphore. And then it's assigning this local variable to the current pose, and then it's done. And then it goes on and uses that local copy to plan its trajectory to do to go to the destination. So this one is how it's being set every so often, and then this is an example of how somewhere else in the code from the main task is using that. Is there any question about that? And here's the main again. I just put this back in here to show you. This task is started and it runs for the whole length of the program, the localized task. It stays running until the end. And then this is where I showed you that go to destination is right there. So here I can show again. So, well, I guess this is just while the system is running, it is doing the localize all the time. All these other behaviors are happening at the same time, essentially. Well, they're given terms, okay? It's not literally the same time, but all of these movements here are being done while that localize is still running every 50 milliseconds. But I didn't have to code it in a big, long, single routine like you do with the Arduino. Anyway, any other questions about that? How are we doing time-wise? All right, I'm almost done. Or a little more, but there's any questions about that? Or you want to see anything else? Hopefully this is interesting. So the other project I wanted to just highlight is a totally different language now and a totally different hardware. Microbit, make code for microbit is the standard tool, a standard program you use to program the microbit, which is a wonderful $10 card. It looks like this one on the right here. And a bunch of us used it in the McQueen robot, little two-wheel, small little robot that you can that uses this card as its brain. And microbit, or the make code in this case uses make code has a choice between blocky, like a blocky type GUI interface for younger programmers, or you can program in JavaScript. Technically, it's TypeScript, but which actually has types as opposed. It's strict typing as opposed to JavaScript, which is not typed at all. You just say A equals whatever. You don't have to tell the type, but so it's a little more strict, which is probably better in my opinion. So this also has a runtime. Let me disable that thing. Or I don't know if you can see. I keep getting these rest break. The JavaScript that in MakeCode that downloads to your microbit has a runtime with a multitasking built in. So it's another simple multitasking, but it's quite easy to use. Probably even easier than that robots see. And here are some of the basics of it. So the basic dot forever is like one of the main lines or keywords that you use to program it. And this essentially, you define a function inside there, and that adds a task. Essentially, that's a task to run this function over and over forever, and giving control to other background tasks between runs. So at the end of this function, the runtime automatically gives control to some other one. Now this other one, in background function, that's the same thing really. And that is a common, you can use that, except it's not a forever loop, it's just one. You'd have to put in your own loop there in this function. So this will just run it once, unless you have a while loop in there or something. Now there's another, so that runs a task in the background. Now there's these other type of user interface controls. They also are running tasks in the background, or it could be an interrupt, we don't know for sure, but some of them are definitely not interrupts. But when you put in a command such as, or a line of code, on button pressed, button B with a function, that sets up a task, or it could be an interrupt, to keep checking for a button press. And when the button is pressed, then this code gets executed. So that's essentially a task that is concurrent. So here's a code excerpt from my traffic program, LA traffic. The main function is a basic forever, and that's the whole state machine. I won't go into the details there of doing all of the behavior I want, right? So that one is just running continually. Now, here's some background tasks I wanted to do. So I wanted to do this this particular function to follow the line, right? I want to, if I move, I want to continually follow the line. This follow line has to be executed over and over again, really, because that does is it checks to see, follow line checks to see where you are, if you're to the right of the line or left of the line, and that sort of thing. Every using the sensors, and then it will say go right, go left, that kind of thing, right? So this is something I want to always do while the robot's moving. I want to continually follow the line. So in the background, I'm following the line. It's what's beautiful about this whole concurrent model or programming like this is it's just how you would describe it to someone. Like, while I was doing this, I was also doing that. So while I'm doing this, while I'm chewing gum, I'm also walking, right? And this is the walking part. And again, here's a voluntarily give up some time by giving like 25 milliseconds here with a pause. Pause is the same as sleep or wait 1 millisecond in the other system. And now the second task I want to do is I want to randomly stop every 5 to 10 seconds. That's what gives the whole this little game some intrigue, because, or not intrigue, it makes it interesting because the driver, a little car is going to stop in the middle of the road every once in a while, and that's where the fun happens, when the guy behind him beeps at him, etc., or crashes into him. So this is continually running the background, and I just do a pause here of a certain amount of time, and then stop if the when that random amount of time has gone by. I tell the robot to stop, and then I give it a sleeping look. That's its face. So this continually runs in the background while I'm following the line at the same time and doing the main functions as well. And that's all I had to do. You know, now, like, here's one other example. It's a more complicated one, but I just wanted to show you that on event is also something that's going to add a task to the system that's going to continually check to see if an event has come in. Now, these aren't interrupt, almost certainly not an interrupt, because this is, there's also a send event routine. So you can send an event and you can catch an event. But so this event, this is constantly in the system. It's going to, somewhere there's a loop, there's a place where it's checking to see if this event comes once you've given it this code, it's going to check, and when that event arrives, then I run this code. This is to detect a crash, to detect a deceleration of 2.5 Gs. And but so this is essentially another task is being managed in the system that has to be continually called. But I don't have to do this all in one loop. It's all nicely separated for me. And here's the video. So there he goes to sleep. That was the sleep one going on, and this is following the line all at the same time. Falls asleep. I didn't show you all the other code, but here's a crash coming up where we'll execute that on event, the 2G detect 2.5 G detection. And then he makes that high-pitched noise. That high-pitched noise was the crash, actually. So
I like the angry phases.
Yeah, you got to have the angry. Yeah, so it was a fun project, that or mini project, I guess. But so that's the end of my slides. Is there any questions about that, or any insights from anybody who would like to share? Let's see how many people we got.
Yep. Thanks. On the chat, I posted just coincidentally the Nuts and Bolts magazine had an article on a real-time operating system for the Arduino, believe it or not. So it's something that wanted to check out. But basically, essentially, exactly what you're talking about here. So, as a library, you can install.
Oh yeah, I haven't seen your. Oh, okay, I see your chat now.
I just can't believe you could fit all that on an Arduino, but there it is.
Yeah, it's hard to imagine. It's amazing how they can, free RTOS. Yeah, I'll have to check that out.
Yeah, same thing with a cooperative. There's a function you call. You can't call delay because it doesn't give up cycles to the other tasks. They have a special delay function that does exactly what you were talking about.
Yeah, so I mean, I had a lot of fun with this. I mean, the hardest project I think I've done really in the last few years was this CAN one. I mean, this thing had a lot of tasks, a lot of code. I mean, localization by dead reckoning. There's a lot going on there. If I didn't use tasks, it would have been difficult. Even much harder to program, I think. All right, well, I'm going to stop share. And there I am. All right, so.
Yeah, so Jim, you covered a lot of topics today about how to get a robot to do more than one thing at once. So a lot of the kids in the audience today are used to smartphones and computers with lots of computer cores that just naturally do a bunch of stuff at once. But there was a time when computers could only do one thing at once, and they had to come up with some clever ways to emulate or pretend you could do more things at once. And so there are so many topics that you touched on between cooperative and preemptive multitasking, the concept between multitasking and event-driven programming. I know we've got at least a couple of people in our audience where this is new to. Now, one of the last topics that you touched on was event-driven programming. Can you briefly touch on the difference between that and the two different types of multitasking that you did, the cooperative and the preemptive, and what makes event-driven programming different?
Yeah, I mean, I guess I hadn't planned to. I guess that was sort of, yeah, a little bit on the at the end, or just a touch of that, of event-driven. But in the old days, you had to have a main loop, for instance, to handle all your events. I mean, this is still done in some situations, and that I even work on with embedded systems. But in the old days, if you have event system. An event system means that something happens, and you want some other part of the code to know about it. So you have a queue of events, like a mouse moving. It goes back to the basics, right? Someone moves a mouse, or you need to track where it's moving every so often, like every 10 times a second, say. And so those are events. Or the mouse clicks, that's an event. It goes into a list, a queue. If you click 5 times, it saves those 5 different clicks. And then messages get queued up in a list, and then those have to be, then someone is interested in that information, they subscribe to that. It's a publish subscribe. It's very similar to what's in ROS, actually. So in the old days, you had to have a big long loop that would check, say get next event, and then it would be, that routine would get the next event off the queue. If there was 0 events, it would just wait there forever. And then as soon as an event comes in, it would then, it will go start executing code and find out, okay, which event was it? Okay, it was a mouse click. Okay, I know how to process that. And then it would do something with that click and start to work with it. So that was a big long loop. And then you'd say, if mouse click, else if something else, window is enlarged, or blah, blah, blah. So that's the old way to do it. And what you can, I mean, with the cooperative, essentially with multitasking, you still have a queue with these events. You'll still have a queue of events, and you'll have to get the next one off the queue. But so that's like a different kind of a system, really, than the preemptive and the different kinds of, well, yeah, preemptive and cooperative. So event-driven is ability to is essentially having that queue of events, and you could have multiple queues too, and one piece of code can subscribe and another can publish, and those could be different tasks that are working within the preemptive multitasking system. So it's that kind of event-driven system exists within these multiple tasks that are running, if that makes sense. It's kind of used by the different tasks can use an event-driven system like that. Now, in the case, the example I gave, where you have, like, you're waiting for an event in this runtime system, where, like I showed you for the BBC microbit, when you add an event like wait for button B to be pressed, that actually is being inserted into some kind of list of the runtime in the runtime to go through and check. So it's just making it easier for you to as a programmer, you don't have to have a big long loop where you check every single one. You just put in the on event call, all the on event calls that you, all the on event, I'm sorry, routines that you want, and the system compiler essentially takes all those and puts them into a list, and then it does the loop and it checks to see as an event comes in, it sends it to the correct routine that you've provided. So that's, you're kind of, you're participating in the this multitasking loop essentially by just declaring your event handlers. Does that make sense?
Yeah, that's pretty much it. It's two different approaches to how to get your code to do something, right? So most of us have written Arduino in C code, and if, for example, you know, you wanted to see if there was a signal on the line, and Arduino 101, if you wanted to do something when you saw a signal on the line, you could write a program that looks for the signal, and then if it's not there, then look for it again, or look for it and then pause and then go again. So this is what's called polling, right? So you've got one program doing one thing, and I'm going to make sure B happens after A by checking for A over and over again. So I'm polling and running this program loop, and when I see this signal, then I'll trigger my action. Great for simple programs, very straightforward. Hopefully a lot of us have heard of the concept of an interrupt, right? So you can set up a pin on an Arduino that when you get a signal on it, the Arduino stops what it's doing and it goes over here and it runs some other code. In event-driven programming, you're still writing code that does something, but instead of polling and waiting on your own and tying up the processor and tying up cycles, there's some framework in, let's say, your host operating system or in your host firmware that does that for you. So instead of writing a piece of code that says, is it here yet? Nope. Is it here yet? Nope. You'll be able to like basically say, hey, operating system, you tell me when this pin has a signal. And with interrupts in Arduino, it's actually, you know, pins going high and low. But at a higher level for programs, these are messages that are being passed around. Like Jim said, there's a messaging queue and all of this stuff that goes into it. And what's nice is that you can write some code. You can say, hey, OS, you wake me up when this event passes. And then your little piece of code goes to sleep. And then when that event is seen and it matches the criteria, you're woken up and you can do your work.
Alan.
Yeah.
This is what you have to recognize that if you're going to use an interrupt-driven system, that the processor has to be capable of accepting interrupts. So that's a hardware kind of thing that's used in conjunction with software.
Yeah.
Correct. Yeah. So on the Arduino, if you're familiar with interrupts, it's a nice way of thinking about event-driven program. Now, of course, in event-driven programming, there's not actually a hardware interrupt that, you know, it does it, but when you're trying to wrap your head around when code runs, whether I run all the time and look for something, or I just sit by and then the operating system taps me on the shoulder when it's ready, it's a nice abstraction, a nice way of looking at the differences.
I wanted to mention something that Alan and I had discussed a few meetings ago about preemption. And it relates to what Carl was bringing up about real-time operating systems, is that, you know, not all preemption is equal. And I misspoke when I was talking with Alan, and I was correlating like a real-time OS preemption with just preemption. So if you have like a Linux system, yes, it's preemptive. The scheduler can kick one task out and bring in another, but real-time OSs are a special breed where they can respond to an interrupt, and it doesn't go necessarily to like an interrupt service routine. The real-time kernel, when an event like an interrupt happens, it can virtually instantly preemptively schedule associated task with that. So that's sort of like the ultimate combination of interrupts and preemption.
Yeah, for sure. There's a
That's
lot.
interesting. Yeah.
Yeah, there's a lot to take in, and for those of us who are getting started on, Arduino, where if you get to do one thing, it's a sense of accomplishment, which is great. When you find you need to juggle multiple things, there's some purists here in the audience that I'm sure that know that, okay, well, I don't need a multitasking operating system. I can just write a main loop, and I can pull, and up to a certain point you can do that. But there's as Jim had shown in some of his sample pieces of code, once you move up to that next level and take advantage of Robot C or FreeRTOS or any one of these kind of firmware overlays that give you some more tools to set up, hey, this is a task and this is how much time I want it to run. It solves way more problems than it causes when you get to writing more complex code. It's exciting.
Yeah, I can't. I mean, I can't speak any more higher of it, because it's just really, it really is such a relief when I had to I used the Arduino and I did what I could. I had that main loop and I had to do all this stuff to get that robot to go around the colored line following, right? And it you kind of get into the mode of, okay, it's a single loop and I'm just gonna go with the flow here. And then maybe you get an interrupt. Like I tried the interrupt for the color thing. It didn't work out in the end, so I ended up just using the fastest synchronous color integrator or color detector. But you could have used an interrupt, which can help you. But then when I got to the doing localization and all that stuff, and go, oh, tasks, I gotta use tasks. It's something, I don't know, I'm a computer science background, so parallelism and all that is sort of part of the fun. But it turned out to be pretty useful, I think, making the code easier to work with when you've literally got multiple things to do at the same time. You can abstract it in your head. You can go, I don't have to worry about that thing, it's running. And the only thing you have to really worry about is when you need to communicate from one to the other. And then I showed a simple example of that, but it's really nice to not have to think always everything in all these different operations in this serial fashion. Like you are the PC counter in your head, having to go through that. Whereas you can abstract it and say, that routine is on its own. I don't have to think about it. It's working. I started that task. It's going to run until I stop it, and I can worry about other things going on. Anyway, enough. I'll get off the soapbox.
Well,
Yeah.
I do have a question though, Jim. So which do you prefer? Is it the task-oriented or is it for the Arduino? I mean, could you do it on the Arduino, or is that just I'm not following entirely on that.
Yeah, well, I showed you the, I haven't used it, but well, this Robot C actually has an Arduino version that's free. You can download it, and it can do three tasks at once on the Arduino, for instance, whereas my Lego NXT can do 10 tasks at once. So that's a hardware limitation, essentially, or but hardware / firmware or whatever. But you can make any single processor work with concurrency if you just set it up properly. And the easiest way is through someone else's code, like this free RTOS sounds like a good way. But when I'm working on Arduino, though, I have only programmed it the traditional way. I've only done just a single loop and just done it with a state machine in there, or have well, just one thing after the other. Process, look at the IR, look at the sensor, make some decisions, and then move the motors, and then repeat the whole thing. And then do a lot of debug printouts send them to the Bluetooth so you can see what's going on.
Okay. Well, thank you.
Yeah, I prefer if I have the ability, I will use a multitasking. Yeah, at this point, I haven't hit up against a situation where you're running out of memory, or in a certain type of, like the Arduino, it's gonna be it's not a clear answer there, because your hardware is so low powered and everything, and so low memory that you may not really have the choice. But even this software from 2015, it's got you can do 3 tasks at once, so I'll take that.
Yes, I see what you're saying. Okay, well, thank you.
Thank you.
Thanks, Jim.
Thanks.
That was a very good talk.
Yes, thank you.
Okay, so we were supposed to have Sergey do the second half, but we ran the entire hour. Sergey,
sorry about that. He was going to go pretty quick.
how do you guys want to do this? You guys want to use the rest of the half hour for Sergey, or?
So Sergey, I have a proposal. Sorry, I texted you, but it must not have gone through. We promised you 20 to 30 minutes today, so you could fill us in on stuff you've been working on.
Mm-hmm.
And if you'd like to take advantage of that, the next half hour is yours, no problem. However, I suspect that just like Jim, you've been up to far more than can fit in a 20 or 30-minute talk. So another option would be just to put you in as the guest speaker for our next meeting, so you have a little bit more time, room to breathe, and we can ask you more questions.
I believe Dr. Bruce is doing next meeting.
Dr. Bruce asked us to cover it, didn't he?
Are you sure? I think it was this one.
It was August, wasn't it?
Yeah, I believe he said, please cover me for that one.
Okay,
August.
then yeah, Sergey, if you want, you can have that hour.
Actually, I have a very short presentation, so I will not bog the audience for very long. Can you hear me? I have different camera now, so I don't know.
Yeah, we can hear you.
Yep, loud
and clear.
Yeah, I'm just playing on the space bar here, but you should be able to hear me.
Yeah, we can hear you.
Okay, so can I share my screen? How do you want to?
Yes.
Yep, so Sergey, when you're ready to share your screen, on the bottom of the Zoom application window, go ahead and click on the green share screen box. And from there, you can offer to share your entire screen, and we'll be able to see what you're seeing.
I see select a window application, but I don't see the whole screen.
Yeah, the left topmost option is share screen. That's the easiest one to use.
Yeah.
I need the screen actually, so let me do portion.
Yeah, you can do the full screen. One of the options there, it shows you the regular applications, and then it has like another little tab kind of thing where it shows screens. One of the options is screen.
How are you feeling, Ben?
Okay, yeah, we see your whole desktop now.
Yeah.
Perfect.
Your mic is mute. Sergey, your mic is mute.
Unmute.
There you go.
Okay, sorry for that, usual setup problems. Okay, I'm doing a lawnmower. It's outdoors, and I don't want to reinvent the wheel. That's the kind of initial arguments, initial conditions that I'm facing. So obviously, when you get through the hardware and you know, kind of figure out how to radio control your robot, now it is about architecture and what's available, what building blocks are available for you to play with and ultimately to build your system. Now, what I want to build is actually already built many times. And this is one of the examples that I lifted from the robot building company. The architecture I'm looking at is based on the autopilot. And on top of the autopilot, I want to use some kind of, you know, ROS hosting hardware, in this case, Jetson Nano. And the separation of tasks between these two will be that the autopilot will be doing the routine tasks like following the line, going to the waypoint. Yet again, we are outdoors. Reading GPS and sending it where it needs to be, you know, processed. The high-level operation, the NVIDIA Jetson Nano, will be looking through its camera at the obstacles. It will be doing obstacle avoidance. It will be recognizing anything that needs action, and it will be running a lot of Python scripts, maybe even planning those waypoints for the lawnmower to execute. So the next slide is, what do I have in terms of autopilots? I can have one of two very well established autopilots code bases. They are open source, so I can compile them and run on the hardware that they support. One is ArduPilot and another is PX4. There is hardware that is available for drones, and it is about $70 on, you know, eBay or wherever you buy hardware. There is also an option to run it on Raspberry Pi. I like the Raspberry Pi option for many reasons. There is PX4 supported branch that runs on Raspberry Pi, and it can be cross-compiled and basically downloaded into Raspberry Pi, and it will behave kind of exactly like this thing here, the actual hardware that is made for running autopilots. Now, when it comes to controlling the robot, you need a ground control software. So ground control software runs on your laptop, on your kind of something that you have in hand. Some of the options are running it on your tablet, on Android, for example, or iOS. There are a lot of professionally made, kind of highly paid, highly priced options. But there are two free options, and I use them both, Mission Planner and Q Ground Control, and they're excellent in different ways. You know, Mission Planner looks a little bit more kind of unpolished, but it does the job and it has its own, you know, features that I like. Q Ground Control is absolutely polished, wonderfully looking, and very easy to use ground control software. When it comes to communication between the ground control and your robot, it's done through the protocol that is actually close to ROS in a way. It's a publish subscribe with all the little things, or actually bigger things, that allow it to work through telemetry radios like this, which don't have a lot of bandwidth. I mean, obviously, if you have your robot working closely within your Wi-Fi range, you can use your Wi-Fi, no problem at all, especially on Raspberry Pi. But if your robot, I mean, in this case, drone, for example, for telemetry, flies a distance about a couple of kilometers, you need a radio like this, and one of these radios goes into your laptop, connects through USB, another is going into that Pixhawk that I showed before, or it can connect to Raspberry Pi as well. And voila, you have all your messages, ROS-like messages that now come through these antennas right under your fingertips. Now that's pretty much it when it comes to the slides, and now I'm up for a little demo here. What I have on my Windows 10 computer is PX4 firmware, which is compiled for Linux, for POSIX, for Cygwin in this case. Cygwin is the system that allows you to run Linux almost natively on a Windows computer. So I use it all the time, and it's a good choice for, you know, playing with things on your main computer. Now what I have here is a little command. I will read it for you, just it's too small probably on your screens. Make PX4 CSULB, which is the simulation kind of simulation configuration. And run JMAVSim, so it's Java-based simulator. So I press carriage return, enter. And here is the PX4 that started in my screen. And you now see the drone, which is actually sitting in my lawn. And I have a proof that it is sitting on my lawn.
Hey, Sergey.
Yes.
On the command line, if you do hold down Control and do the mouse wheel, it makes the font bigger.
Okay, there is not much on the command line to see. I don't want to mess it with, because sometimes it's a little finicky, you know. The interesting part about this command line screen here is that I can press enter, and there is a terminal for PX4 control. So I can enter the commands for the drone, like takeoff and whatever. But it's obviously not the best way to control the drone. So what I'm going to do is type QG ground control in my search window, and hopefully everything comes up and connects. And this is the position flight mode. You can hear my ground control talking, right? So let me see. Hopefully I will not mess the communication between the two while resizing windows and moving them around to fit into the area. Okay, what it wants now. You can see my loan. This is the big loan. This is the loan that I actually want to mow. And let me move that around a little bit. And there are options here, different screens. For example, I can set communication links here. I can look at Mavlink, which is the protocol between the two components, between as many components as you want, actually. And I can see the planner, mission planner, so I can put the waypoints where I want them and, you know, to do the job. And I can actually fly the drone. When I fly the drone, it wants to offer me start the mission. I slide it, and now what is mission going to do? Mode. He says mission flight mode. Armed. And now you can see here the altitude will be increasing. And the drone is flying. Now what it is going to do is to climb to 50 feet, I believe, and then to go waypoint by waypoint. And of course, I can return and land and do everything I want in that case. But let me make it return at this point. I don't want to take too much time executing return this flight mode. Little
This is like a full simulator then of drones, isn't it?
Yeah, and you can, it doesn't require any hardware. It doesn't require any, you know, specifically big computer. You can run it on your laptop in that simulation mode if you want to play with it and stuff like that. Meanwhile, while it is very slowly landing, what I want to show you is how the Mavlink looks like. So this is communication that is taking place between the drone and the ground station. Ideally, it will be taking place over that radio telemetry set. But in this case, of course, it's going over the local network, actually within my computer. But I can go over the Wi-Fi. I can go over the router that I have here, wired with Ethernet or whatever I want. I can, for example, read the position of my drone right here. You can see the actual latitude and longitude here. I can see altitude. I can see heartbeat. I can see battery status. And that's just, I can plot any value, and a little graph will appear here and stuff like that. So this is your insight into the communication between the drone and you. And if you have anything to debug, any algorithm that you put on top of your planning, of your mission plan, you can see how it is executed here in terms of the Mavlink communication. Let's plan, it just brought the message flight plan complete. And what I want to do is I want to remove that little plan from the vehicle. And let me show you how the planning can be done here. So now I have my vehicle. In this case, it is a drone, but who cares? You know, it can be my lawnmower or it can be one of my robots, you know, outdoors capable two-wheelers, tank drive, and, you know, Raspberry Pi running autopilot. And I'm sitting here connected to it through my Wi-Fi that reaches out. So I'm starting with the blank mission, blank plan. And what I want to do is I want to take off. And then I want to add a waypoint, for example. So I can add a waypoint, and I have a little control over the altitude here. For example, instead of 50 feet over the ground, I want to have 5 feet over the ground, and you know, that makes flying much faster. And then I can do waypoint after waypoint like this, and that will basically create a loop. And then I hit return, and that makes the drone to return to the starting point. I can now upload it, and I can fly it, and you will see it flying here. I don't know if it is worth demoing. It's extra 5 minutes. But what I wanted to show you actually is the other capability of this planner. Look at that. I can actually have a survey of the area.
Manual control lost.
Uh-oh, I'm in trouble. But anyway, probably I'm not in trouble. But anyway, what I'm going to do is I'm going to build a polygon right here, which is my lawn. And it can be very complicated form, you know. I mean, I can add, for example, a point here and drag it, very convenient, right? Now, what I want to do is I press done with polygon, and now I have the survey here. Altitude will be 5 meters. Trigger distance 1 meter. Spacing will be, let it be 5 meters. I want my lawn to be tiger striped. Angle, that's a different thing. Turnaround is how far I want it to go beyond the polygon that I drew. So I want it tight. And here is my 5 meter scanning of that lawn. I can do a 1 meter spacing, and it will be like this. So 1 meter is 3 feet. That's a little bit less than the lawnmower takes. I mean, it mows theoretically 54 inches. It's 1.5 meters, but I mean, you have to mow twice. But anyway, that's how it goes. Angle, I can, for example, specify 30, and it will mow in this direction. Now, on top of that, you remember that we have 2 ways of controlling extra functionality. For example, I have a tree here in the middle of the lawn, and I have to obstacle avoid it. I have other little brushes here and there and I have to do obstacle avoidance. That will be taken care by NVIDIA Jetson Nano and its cameras and everything else through Python code. And obviously, Jetson Nano will be interfering with the mission and then resuming mission when it is safe to do so. Now, the next thing I can do is I can plan that whole thing, avoiding the trees by using Python code that runs on top of the ground control. So there is a Python interface in the ground control application here. So I can run that. And also I can generate missions on the side by using any code I like, C# or Python or whatever, by reading this mission and correcting it, inserting waypoints, deleting waypoints, doing whatever I want with that mission, because it's just a JSON file, and you know, I can do whatever in programming with JSON files. That concludes my presentation. I will do the spacing, let it be 5 meters. And I will upload it. And hopefully I will be able to fly that mission. I'm still connected.
Mission flight mode. Armed.
It will be taking off. Yep, it does. And it flies too high at this point, but I don't care. That's the end of it. So let me unshare the screen. And any questions?
Hey, Sergey, that is so cool. I know you always talk about how you haven't accomplished a lot, but that is a lot of ground to cover. What are, what you had mentioned, you are looking at maybe putting this into a lawnmower or a drone or what? What are you looking at doing next with this? What's your next step?
Well, my next step is cross-compile the PX4 code into Raspberry Pi. There is ARM cross-compiler on a Linux computer here. And I have to use Linux because they don't set up, they don't have a ready-to-go setup with you know, Windows cross-compiler.
Yay, Linux.
And then I will have to configure it for the ground drone that I have, the two-wheeler that is capable of going through the grass. And I will be making it to execute, you know, the mission that I just showed you, you know, striping the lawn or whatever I load. And then as I go, you know, that will be more complicated missions, obviously obstacle avoidance and, you know, everything else. I don't plan that far, you know.
Cool.
It can do the obstacle avoidance, like you said, automatically. That task is running on board, right? With the AI. I mean the NVIDIA.
Jetson.
The Jetson.
Well, I have to obviously train Jetson Nano to do obstacle avoidance in certain way that is, you know, applicable to my load specifically, trees instead of the, you know, kind of cabinets that I had here. But
Right.
also I want the very organized way of mowing the lawn. Otherwise it will be kind of messy and I don't want that. So there will be a lot of Python programming, and I have to learn Python yet. I haven't done much in Python. I'm cutter and paster, you know, copy paster type of guy.
What will your Python code have to do? I mean, it looks like the you have that plan that you just showed us was the whole pattern and the angles and everything. That's doesn't require any more code, right?
Well, I might need to correct that plan for known obstacles. For example, it doesn't allow me at this point. I mean, I can have a fence, for example, set up in the middle of the lawn, but I haven't seen yet the mission planner type, mission planner algorithm that is built into the Q ground control to actually avoid that fence. So I might have to do it myself. And of course, I have to connect that NVIDIA Python code through Mavlink Python interface into the communication system of the, you know, of the autopilot of the PX running on Raspberry Pi.
Right.
Cool.
Awesome, Sergey. Like always, thank you.
Thank you.
Excellent.
Okay, I think there's only one show and tell. Thomas, you said you had a short show and tell?
Oh yeah, can you hear me?
Yes, we can.
Yeah, this is just real short. I just wanted to show off my robotics coffee mugs. Oh wait, I gotta take off the background.
Yeah, can you please?
There we go. All right, the first one I wanted to show you is this one here. It says, I just want to drink coffee and build robots. That was a gift from my wife last Christmas. Yeah, everybody see that? Isn't that great?
Yeah.
Wow.
Nice.
It's like custom made. I mean,
I think that came from Amazon.com. And second, I want to show you my BB-8 mug. Just a plain old mug, nice size.
Cute.
And lastly, I wanted to show you my, what's the name of this robot, somebody?
Walter?
Walter, come on, you're the guy.
I think he built one of those.
BB9E, I think.
BB what?
9E.
9E, all right, that's the BB9E. It comes with a little top so he doesn't get too, or coffee doesn't get too cold. If you turn it,
That's cool,
and
Thomas.
nice.
that's the end of my presentation.
Thank you, Thomas.
Low tech.
Low tech.
We like that.
Gotta want it. Oh, can't really show it.
Well, it looks like we ran over just a tiny bit this time. So if anybody else have anything else to add or anything? Oh, what is that?
Yeah, Ben, this is Buzz. A quick question. I tried to find the recording from our previous meeting on the 10th of this month, and I didn't find it anywhere. What's the story on that?
Someone's really dragging their feet on uploading those clips to YouTube, aren't they? I'll talk to that guy. Oh,
I know a guy.
Oh,
He's
yeah.
got multiple personalities.
So, apparently, I'm not losing my mind after all, huh?
No.
No, Buzz, you're not.
On the crack.
Hey, guys, I just got my Yoda back together after being painted.
Yay.
Working on the arms. The only thing left I got to put on.
So, Ben, again, back to the recordings. When might this one be posted?
Oh, I'll talk to the guy that posted. He should have them both posted this weekend. Oh, yeah?
Yeah,
Okay,
I'll talk to the guy.
Yeah.
Should have been.
Yeah, hopefully this
Over
weekend.
there.
Hopefully this
Well,
weekend they'll be up.
It's a little work, right? I mean, you have to, yeah.
Well-
Don't worry, we're like the homebrew club. They didn't post their first one for like weeks. I had to. we're past that. We're pretty good.
That's right. I gotta
Well,
make time to join that one.
I got to tell you, I really appreciate having access to those things, to be able to review things. And also when I'm having trouble logging on and I get to the meeting late and all that because of my silly computer, having those recordings are just superb. Thank you.
Yeah, they're useful. Yeah,
for sure.
Okay. I guess that's it for this meeting. Again, we meet on the 2nd and the 4th Friday of every month at the same time, same link. So maybe see you guys again next at the next meeting, which would be, let's see, on the 14th. Oh, and there is no.
Oh, that's great.
Yeah, and there's no 4th Friday that month.
28th.
That's why Dr. Bruce wanted someone to cover for him. I get it now.
Oh, yeah, okay.
Oh, okay.
Why?
What's on the 28th?
28th is the
2nd, 3rd, 4th. Yeah, the 28th is the
28th is the 4th, right?
Yeah.
There's just there's the second one. Yeah.
Yeah, there is.
Oh, Dr. Bruce wanted to. Yeah, well, because he wants to go once a month, right? Isn't that what he'd like to do?
Yeah.
Yeah, and we'll figure it out. We'll have a sidebar to make sure that the next 2 calls are filled with speakers. But yeah, because he asked during the first meeting of July if someone could cover his slot in August, right?
In August, yeah.
Yeah.
And then I mentioned, hey, we have one next in 2 weeks too. But anyway, yeah.
Yeah, we'll figure something out.
Yeah.
Well, if you need somebody to do something, yeah, I can probably do one or something at some point.
We have a bunch of members who are doing a bunch of really exciting stuff. It shouldn't be hard. We just have to sweet talk them into it.
Yeah.
Yep.
We can continue this in our Google groups.
Yeah, we'll talk about, see what people are up to.
Yeah.
Great.
All right, guys. Have a good one.
Hey, Thomas.
Enjoy your weekend. Stay safe.
I will.
Good to see everybody.
Yeah.
You get better, Ben.
I'm trying.
Oh, are you under the weather?
I had an accident kind of thing, and
Oh.
Oh,
yeah, it's all right.
Yeah,
sorry to hear about it.